Dask Delayed is a simple and powerful API that lets you build out custom computations with normal Python code. It's often used to parallelize existing Python codebases or to build out more complex algorithms. In this example, we're going to play with a simple algorithm and then build out something a bit more complex later. Dask Delayed is also different from other APIs like dask.dataframe or dask.array in that it doesn't provide automatic algorithms for you, but it gives you full freedom to build your own. So in this example, we have three functions, increment, decrement, and add, which add one to a number, subtract one from a number, and add two numbers together, but sleep for a random amount of time to simulate work. In your workflow, you might imagine this as load data, process data, combine data in some way. So I have some simple Python code here that runs these three functions in sequence. This will run anywhere between 0 and 3 seconds in parallel. Sequentially. That's because Python runs this code sequentially, one line after the other. However, we can see that there are some opportunities for parallelism here. In particular, this increment and decrement function could be run at the same time. This add function depends on both of them, so it definitely needs to be run afterwards. So let's use Dask Delayed to parallelize out this workflow. We're going to use Dask Delayed as a decorator around our functions. This decorator will make our functions lazy by default. This means that when we run this code now, it will return instantly. It only took a few hundred microseconds. That's because it actually hasn't done any real work yet. Instead, this value z is a Dask Delayed object. And if we want to, we can look at what that object is internally by calling the visualize method. So this z object has recorded all of the calls that are necessary in order to produce its final result, and it's showing you them here visually. It knows it needs to call increment, decrement, and add in order to produce the final result. So let's go ahead and run that. Dask Delayed, as with dask.dataframe or dask.array, is lazy, so you need to call .compute at the end to get out a concrete result. So what just happened there? We called increment, took 200 milliseconds. At the same time, we were also calling decrement on a separate thread. That took 600 milliseconds. Then we communicated the result from one to the other, this very thin red bar. Then we added the two together, taking around a second. So what's nice here is that we got some parallelism, but we also got to track dependencies with add. Notice add didn't start until both increment and decrement had finished. So this is very useful if you want to parallelize out existing Python code. Here's more or less the same code, but now run many more times. So now we're using many more threads on our machine. This machine has 12 cores, so it's using 12 threads. So Dask Delayed can be very useful either for very simple, embarrassingly parallel operations, or for more complex computations, like what's below. So now we have 128 values sitting in different workers, maybe across a cluster. Let's say we wanted to add up all of those values together. One way would be to bring all of those values to one machine and then call sum. And another way, we might add up every neighboring pair of those numbers. So if we have many numbers here at the bottom, we might add up neighboring pairs and produce a new list with half as many numbers. We might keep doing that until we have only one number left. This is often called a tree summation. Libraries like dask.dataframe and dask.array already have these built in, but if they didn't, we can use Dask Delayed to build it ourselves. So this tree summation is encoded in the following Python code. You don't need to understand this entirely right now, but maybe let's look at a couple bits of it. We're adding together neighboring elements of this list, and we're going to keep doing that while that list is of size greater than 1. So what's nice is that we're able to build out a fairly complex algorithm, but with only a few lines of normal-looking Python code. You're able to execute that algorithm in parallel. You can almost see sort of the tree structure here coming off on the right. At the beginning of the computation, we have a lot of work to do, so we can saturate all of our workers. But towards the end, there's less work to do. There's only a few things towards the top of that tree. Let's watch that computation again, but looking at the Dask graph as we're executing. So you can see here the Dask internals as executing all of those tasks and finishing them as we go. And again, what's nice is that this graph was entirely determined by these 5 or 6 lines of Python code. So this shows you that you can take normal Python code and use Dask Delayed to build your own algorithms. This is often used in practice. So this is an example of the task graph from the risk model of a large retail bank. When you go to apply for a credit card, they run lots of functions on you, and this is the complex web of functions that they run. So this shows you the sense for how Dask Delayed gets used in practice. It's often used for very complex situations. If you want to learn more, you might look at Dask Futures, which provide a very similar API, or into how Dask Delayed can integrate with other collections like data frames and arrays to get the best of both worlds.